So today, I'm going to talk about all the things that we have covered before in the last three lectures. And I will mainly focus on the zero vector and zero vector space, which was coming up in the last lecture. So let's get started. But first, we'll solve the DPP that we had yesterday. So anybody can tell me what's the solution for this? Okay, so one of the solutions that I have is 1, 0, 0, minus 1, and 0. Okay, let me write it rather like this. So Rohan is saying that this is one of the solutions, which is correct. 0, 1, 0, minus 1, and also this 0, minus 1. So you will see the formal method of finding these vectors later in the course, but this is how you can solve it, or this is how I would have solved it. So I have to, so the question given to me is that I have to find a basis for a subspace of R4 where all the vectors are such that their components are added to 0. Okay. So what I can do is I can take my vector to be of form this. So A, B, C, 3 vectors, and then I can say it should be um, this particular thing is minus of this plus this, right? Actually, let me take it to another screen. So I'll say I will start with this. So my vectors should be of this form. Yes, so it needs 3 vectors, and it's the dimension of this vector space will be 3. That is correct. But this is how you can find it. So now I can break it down like this. I can break it down like A times 1, 0, 0, minus 1, plus B times 0, 1, 0, minus 1, and C times 0, 0, 1, minus 1. Fine. So if I do this, you can see A and minus A. If you add all the components, it will be 0. B minus B. If you add all components, it will be 0. And C minus C, all the components are 0. Okay. So this is, so now these 3 can actually be my basis vectors. Right. And like someone already said on the chat that dimension of this subspace is equals to 3 because there are 3 linearly independent vectors in the basis of the subspace. Understand? Okay. Fine. Okay. So what's in for today? So we'll quickly do a recap of everything that we have learned so far. And I'll specifically talk about zero vector and zero vector space while we are going on. And that's it. And we'll solve some questions. Fine. I actually wanted to start something new, but I think we needed some sort of revision. So we'll do that today. And from tomorrow onwards, I'll start a new topic. Cool. Let me start with, so first of all, in the first lecture itself, I introduced something called as vector, right? So what is a vector? Can you guys tell me what is a vector? So vector is an entity. Yeah, vector is an entity with magnitude and direction. Okay, and we saw a space where I showed that in linear algebra, vectors are usually rooted at origin. So suppose this is 2. This is the vector. This is the vector 2, 1. where x component of this vector is 2 and y component of this vector is 1. And this is an R2. Fine. Okay, so we know what is a vector. Then we talked about linear combinations of the vector, right? So when we talked about linear combinations of the vector, we saw that, okay, if I have vector v1, v2, v3 that are coming from some vector space belongs to some Rn, then linear combination is basically some A times v1 plus b times v2 plus c times v3, where A, B, and C are coming from real number values, or these are called scalars as well. These are called scalars. And they are coming from real numbers, right? So all such combinations which are coming from this particular equation are called linear combinations of the vectors. And we can have n number of or any number of vectors in this particular set. And when we do a linear combination, we'll just multiply a vector with some scalar and add them to the other vectors. Fine. So this was linear combination of the vectors. So more formally, if x is some vector that belongs to Rn and y is a vector that belongs to Rn, then and a and b are two numbers or scalars which are belonging to R, then ax plus by is called the linear combination of x and y. Fine. So we know what is a linear combination. So this is also done. Now we define span after this. So when we define span, we defined it to be the set of all possible linear combinations of set of vectors, right? So also whatever set I was getting here, right? All the vectors that I generate using this equation for three of these vectors will form my span, right? And I'll call it, this is a span of that set of vectors, right? So span of vectors x and y, where x and y belongs to Rn, is a set of all linear combinations such that a and b are belonging to real number space, right? So we understood what is the span of vectors. Clear? Okay, I'll move on. So we saw what is vector, linear combination, span, and then we talked about linear independence and dependence, right? Let me redefine it for you. So when I said that, so for any set of vectors, suppose I'm taking vectors v1, v2 up to vk, if and only if I can find some ci such that this some ci not equal to 0 and satisfying this equation, I say that these vectors are linearly independent. Sorry, linearly dependent. Or let me just rephrase this. If I have this equation where C1 V1 plus C2 V2, C3 V3, CK VK is 0. Okay. And I only have a trivial solution for this. It means I get this equation satisfied only when C1, C2, C3, and CK, all the scalars are 0. Then only I say that these vectors or this set of vectors is linearly independent. Okay. And if I find that at least one Ci which is not equal to 0 and my equation is satisfied, then the set of vectors become linearly dependent. Okay, so at least one vector is a combination of other vectors in the set that you have. Right? Clear? Fine. Let me take one example to just simplify this so that we understand it. So if I have, say, 1, 0, 0, 1, and say 1, 1. Okay, I'm considering this set of vectors. Tell me, is this set of vectors linearly dependent or independent? This is linearly dependent. Why is this linearly dependent? If I go with this equation that I have written over here, I will take the linear combination. I will say C1 times C1 times 1, 0. C1 times 1, 0 plus C2 times 0, 1 plus C3 times 1, 1 should be equal to 0. Now, what I can do is I can take 1, 1, 0 plus 1 times 0, 1 and I can take minus 1 times of this vector, right? Is equals to 0. So this is coming out to be a 0 vector. 0 vector is coming out to be a 0 vector. This is actually 0 vector and I should not do this. I will do that. So I am able to get non-zero CIs, which are adding this equation up to a 0 vector. So this is linearly dependent. So Ruina is asking, ma'am, in the definition, do we have to mention all VIs not equal to 0 vector? Actually, in definition, we don't explicitly mention this, but yeah, all VI should not be 0. Because if by definition, if any VI is 0, that becomes linearly dependent vector. Okay, so even if say I add a 0 vector here, what will happen? Let's check if we can do that. Because never have I seen a definition where all the VIs are 0. They're not never specified that, but let's check. Okay. So suppose I have 1, 0, 0, 1 and 0, 0 vector, right? So I will do A times 1, 0 plus 0 times 1 plus something times C times 0, 0, right? And I can just take these to be 0, 0 times 1, 0 plus B times B is in 0 times 0, 1 plus I can take C to be anything, right? It'll always give me a 0 vector. It's a 0 vector. So whenever 0 vector is present in any set, okay, it automatically becomes linearly dependent, right? So we need not specify that all VIs should be 0. All it's saying is that given a set of vectors, can you find one CI which is non-zero and still satisfying the equation, then it becomes linearly dependent. So if we have a 0 vector, this will automatically become linearly dependent. Is that clear? Cool. Everybody clear about linear independence and dependence, right? Fine. Okay, now tell me, I think this I already said. A set of vectors containing 0 vector is always linearly dependent. True or false? We just saw, right? So this is true. That whenever I add a 0 vector, whenever we have a 0 vector in set, we can take any non-zero scalar as its multiple and all other coefficients and all other coefficients to be 0. Okay, implies linear dependency. Fine. Okay, moving on. A set S is a set of vectors containing only 0 vector. Okay, so there is a set which I have defined. S is equals to this. This only has a 0 vector. is this set linearly independent? S is linearly independent. Is this true or false? Okay, so yeah, so this is linearly dependent set, right? So this is linearly dependent. This is just another way of asking the previous question only. So this is false. I write true here. Yeah, fine. Okay. Okay. Suppose now another question that I have is set S is an empty set of vectors. Is S linearly independent? So I am defining S to be this vector. Okay. Is this linearly independent or dependent? Think about it. Think about it in terms of the definition that we have seen. Can I find one scalar or one coefficient of the vectors which is non-zero and the equation adds up to zero vector? So true or false? Okay. So this is actually true. Okay. This is true. This is linearly independent. See, there is no vector in this, right? So this is empty set. This is an empty set. So there is no vector. So I cannot find a Ci not equal to 0 such that Ci Vi sum over Ci Vi is equals to 0 vector. Yes, because I cannot have a non-zero Ci. That's why this is a linearly independent set. Is this clear to everyone? I will go back to the definition again. Just this is clear. It's saying that for a set of vectors v1, v2, v3, vk, if Ci, Vi or like linear combination is equals to 0, only when Ci is equals to C2 is equals to C3 is equals to Ck is equals to 0. Means only when I have literally a trivial solution, then I will say that V1, V2, V3 and Vk are linearly independent. Fine. So it means that if I cannot find any Ci which is non-zero and the equation still adds up to 0, which so basically if I can't find any Ci which is non-zero, then the set of vectors will be linearly independent. Now in this empty set, I don't have any vector at all, right? So I cannot even find a Ci which is non-equal to 0 so that it gives me a 0 vector, right? So this set is a linearly independent set. Yes, Rohan, what's the doubt?
Ma'am, am I audible? Hello, ma'am.
You can unmute yourself and probably speak.
Am I audible now, ma'am? Hello.
I'm not able to hear you.
Hello, ma'am. अभी सुनाई दे रहा है, ma'am?
I am not able to hear you for some reason. Just let me be back in a minute. Can you speak now, Rohan?
Yes, ma'am.
Now, yeah. Tell me.
मैम वो जो पिछले स्लाइड पे लिनियरली इंडिपेंडेंट का डेफिनेशन दिया हुआ था ऊपर में.
Yes.
Yeah. So it is saying if we have a set of vectors v1, v2 like this, and only when we have trivial solution, then we can say that it is linearly independent, right?
Yes. Yes.
So for our particular question, if we assume the pi set, the empty set to be linearly independent, then we are assuming after multiplying the trivial solution, the trivial coefficient with it, we'll get the zero vector.
Yes.
But there is no vector in it.
There is
So
no vector in this. So that's why we'll have to come to the second definition, the linear dependent. So we can't prove directly that this is linearly, just a second, linearly independent. What we'll do is it's the alternate way. If any Ci, slides, just a second. Yeah. So you're correct that from the first equation itself, maybe it's not very clear. I don't know what is happening.
then, ma'am, can we assume that for a set of vectors where there are actually vectors,
Yes.
उसमें independent का definition ये ऊपर वाला है और
Yes.
as by definition हम लोग empty set of vectors को linearly independent बोलेंगे. Like by definition, we cannot prove it.
But we can prove that it's not linearly dependent because I will never be able to find a Ci, a non-zero Ci, so that the equation gives me a zero vector.
Okay, so
Using
it's
this, yeah. So this is via the second definition. This definition. Okay.
Yeah, clear.
If any Ci not equal to zero, vectors are linearly dependent. So I will say that I'm not able to find any Ci which is not equal to zero. That's why the set is linearly independent. Make sense?
Yes, ma'am.
Okay. Fine. Where are we? Okay. So I cannot find a Ci not equal to zero such that that's why S is linearly independent. Okay, let's move on to another. So we have covered vector, linear combination of vectors, span, linear independence, and dependence. Then in last lecture, we talked about vector spaces, right? So what is a vector space? So vector space is a set of vectors which follow these 10 properties. And we had talked about these properties in detail. But today I will talk about these properties in terms of a zero space, the zero vector space, okay? So this is zero vector space. Let's see if my zero vector space is actually a vector space. So what is zero vector space? Z is equals to, so I only have a zero vector in it, right? And if this Z is subspace of Rn, it will have n coordinates. N coordinates. Zero vector will have n coordinates. Coordinates is just the number of values that you use to represent a vector. Fine. So this is my zero vector space, which is also denoted by Z. So is this being satisfied? So I only have a zero vector, right? So I will add zero vector, and I can add zero vector in any way. Like I can take zero vector first or the second, doesn't matter. It will always give me a zero vector. I can also do this. Right? So this law is also satisfied. So there exists a vector 0 in this set, which when I add to any other vector in this set will give me the set itself or the vector itself. So yes, I have a zero vector, which I add to the only other vector, which is zero vector itself. I'll get a zero back. Then I should have a additive inverse of this zero, and additive inverse is nothing but minus zero, which is nothing but zero, right? So this is also satisfied. So all these additive properties are satisfied. Let's talk about the multiplicative properties. So I have, if I multiply zero vector with one scalar, I will get the zero vector back. So this is also satisfied. If I take any vector, C1, C2, any two scalars, and I multiply them in any order with the vector 0, I will get the same vector back, right? Even if, I multiply these scalars together first, and then I multiply it to the zero vectors. I'll get the zero vector only. So this is also satisfied. Now, if I have a scalar and I am multiplying it to sum of two vectors from this space, the only vector I have is here is 0. So I will just multiply it with 0 plus 0. And then I can multiply individually with 0 plus 0 and I will get the same vector, which is 0. So this distributive law is also satisfied. Similarly, I can take two scalars and I'll multiply it with 0 and I will also get similar value, which is 0 vector, when I multiply individually the scalars with a 0 vector and add them. So this is also satisfied, right? So all the additive properties are satisfied, all the multiplicative properties are satisfied. Now only two properties are left, which are called the closure properties. So I maybe should write this also. These are additive. These are multiplicative. Okay, I'll write them later. Multiplicative properties. Only thing now I have to check for this to be a valid vector space is whether the closure property satisfy. Okay, so if I take a linear combination, let me take a linear combination with some other this thing. If I take a linear combination, so I will take C1 0 plus C2 0, right? It will give me a 0 vector which already belongs to this set, right? So this is also satisfied. If I take a multiple of 0 vector, it will give me 0 vector which also belongs to the set vector space. So all the 10 axioms which are required for a vector space are satisfied for the 0 vector space. So that's why 0 vector space Z is a valid vector space. Clear? Fine. Okay, let's solve this question. I am giving you a set of vectors where A and B, there are two vectors which belong to R2. And I have defined all the set of vectors to be like this. B is equals to 3A plus 1. Is this a vector space? Okay. So look at this formulation and tell me whether this is a vector space. And if this is not, then tell me the axiom which is not satisfied. At least one axiom that is not satisfied. Okay, what is the other? But I have to talk in terms of, Samir, I have to talk in terms of the axioms. So which axiom is not satisfied here? Okay, no, not closed under addition. Samir, you're right, just that I also need the axiom which is not satisfied. Okay, so let me take some examples. Okay, I have, say, I'm taking the standard basis or standard vectors using which I can construct any vector in R2. Okay, so I've taken these two vectors which belong to R2. Sorry, okay. So what it's saying is my A vector is something. A is some vector. So I maybe take 1, 0, right? And B vector is actually 3A plus B, 3A plus 1, which means 3 times 1, 0 plus 1. Actually, I'm making a mistake. I think this is A and B, right? Sorry.
And A belongs to R2 or A comma B belongs to R2?
It's A comma B belongs to R2. That's what I was also thinking. Sorry, I made a mistake. It's A comma B belongs to R2. Okay, so this vector belongs to R2. Fine, and B is such that, so this vector, so this is the vector. This is 3A plus 1 and this is A. Okay. So all the vectors will be of this form in this set of vectors. Is this clear? Right? Now what is not present in this? If you see, can I ever get a 0, 0 vector in this? So my question is, can I ever get a 0, 0 vector in this set? No, right? Because no matter what value of A I take, there will always be a 1 here, right? Or it will never be like 0. If A is equals to 0 and B is equals to 1. No. So B is I did not get it, Bharat. So I'm always adding 1 here, right? So how will I get 0 here? I will never be able to get 0, no? Here. Yeah, you are saying it will never be a 0, right? So I will never get a 0 vector here. So in my axioms, there was a very important condition that it should always have a 0 vector. So because this 0 vector is not present, I will add one new slide. Because 0 vector is not present. This is not a vector space. Is this clear? Fine. Okay, cool. Let's move on to another question. It's not closed under addition and multiplication as well. I have not checked that, but let me check. Yeah, this will also not have a identity vector, is it? If I multiply it. No, if I multiply it with 1, I'll get a 1. Yeah, this is closed under multiplication, right? This is closed under multiplication. What about addition? Let me just see. Express if I add 2 vectors from this, I will get. Yeah, it's not closed under addition. Yeah, it's not closed under addition, but it's closed under multiplication. -1a. I don't see it. Why this is not closed? Why is this not a why this is not closed under multiplication? So 1x into x, I will get the same element. I multiply with scalars, I'll get the same value. If I add two vectors with this in any order, distributive properties are also satisfied. This is closed under multiplication according to me. This is not closed under addition because there is no 0 vector. And there will also not be a -1 times of this, so that we can add it up and get a 0 vector. Make sense?
Ma'am, can I just ask something?
Yeah.
So we can write this as A13 plus 0, 1, like A into 13 vector plus 0, 1. Can we write like this?
Okay. Yeah.
Now, if we try to like test whether it is closed under multiplication, so
Okay.
what I did, I just multiplied the vector by -1.
Okay.
So I will get the final vector as minus. I got it as -1, -4.
So you're taking A as -1?
No, I'm multiplying entire vector by -1.
Okay, let me see. So my vector is A, 3A plus 1, right? This is my vector. Then
Yes,
I'm
ma'am.
saying this is 3A plus 0, 1, right? And then you're saying this is my vector plus 0, 1, right? Now you're saying
Yes.
if I multiply this whole vector by -1, I should get the same vector.
Same means that that vector should also fall in the same space.
Yes, that is also true. So if I do -1 of this, okay, I will multiply with this. So this -1 will not come here. Oh, yeah, probably. -3 a plus -1, right? Then I
Yes.
have minus a by -3. Oh, it's just what am I doing? -3 a plus 1, right? This it can be, right?
Yeah, it is falling on the same pattern. Yes.
It is, right? It is there. This belongs to space, whatever subspaces is, right? -1 times this. You're just saying that so minus will come out common, right? Understood. I think what you
Sorry
meant
for
was
troubling you.
it's fine. Maybe 3a. No, this will not be valid because it's not the valid vector. Yeah, this is closed under multiplication. It's not closed under addition.
Ma'am,
Hmm.
I think he said right now, a 3a plus 1, this vector, if it is in this set S, after he said after multiplying it by -1. So after
Yes.
multiplying it by -1, the first coordinate is becoming -a.
Yes.
And how can we expect the second coordinate with the rule of this set? A plus 1, like 3 into -a plus 1.
Yes.
So, but
Okay. So you're saying that's why. Now I got it. Okay, cool. Fine. So basically, this will happen, right? So here is -a. So what should happen is B should be 3a plus 1, but a is now -3. Sorry, a is equals to -a. So I have -a plus 1. So I should have -3 plus 1. That's what, right?
Yes, ma'am. Yeah.
Oh, okay. Yeah. Then you were right.
So, ma'am, I think it's then not closed under multiplication.
Closed under multiplication also. Yeah.
Not closed or closed?
Not closed. Not closed.
Not closed, right?
Not
Yes.
closed.
That's what I
Not
was
closed
thinking.
under. Yeah. Thanks for the correction. Multiplication. Yeah. Somebody was saying something.
Ma'am,
Yes.
complete vector a 3a plus 1 is completely treated as one vector x, or else by here you write ma'am a 1 3 plus 0 1, that x and y separately, or else complete vector should be taken as x.
No. So it should be okay. I think I confused you guys. So the vectors are of form this. Okay. So whatever is on top, so vector is defined like this. A and B is the complete vector. So whatever is here at A, below we'll have 3a plus 1, right? So if I have, so the vector is a 3a plus 1. Okay. So if I do a is equals to -a. Okay. So my vector I should get is a minus a 3 into -a plus 1. Okay. So my vector will be -3 minus 3a plus 1.
Ma'am, could you please help me with this vector satisfying that commutative property?
Can you
How
spell?
to?
So I don't remember the names of the properties very honestly. Can you tell me what? Yeah.
X plus y is equals to y plus x.
Y plus x. Okay.
How to check this property with this vector?
So you can take any two vectors. So for example, I have to take vectors of this form. Okay. So I'll take a to be 1. Fine. So my vector will be 1, 3 into 1 plus 1. And then I can take a is equals to 2. So I'll get other vector. So 2,
Okay, got it.
3 into 2 plus 1, 6, 7. Right. So I got 3 and below is 11. Let's do this. Yeah. Okay. So this is correct, right? This property is being followed. If I do the reverse also, it will follow.
Yes, ma'am. Also, ma'am, in that case, before c into x plus y is equals to cx plus cy.
Okay, let's see that. Can you write that? Can you tell
C,
me once again?
C into x plus y is equals to
C into x plus y is equals to cx plus
cx
cy,
plus cy. Yes, ma'am.
distributive property. Okay.
Yeah, ma'am. If
So
we
I will
check,
take,
yeah, ma'am, if we check this property with -1,
yeah, that's what these guys were saying. This will
yeah,
not get satisfied. Yeah,
yes, ma'am.
this will not get satisfied. Yeah, fine. So when I was looking at the question, I only saw that 0 was not present. I didn't do all this analysis. Okay. So thank you for that. But yeah, so this is not a vector space, right? So the answer is no. Okay, moving on. Everybody clear, right? Whatever discussion we had. Okay. Fine. Another question. Oh, okay. This is the same question. I think the slides got reversed. Fine. So we looked at the vector space also. Now let's talk about the subspace. So what is a subspace? Yeah, Rohan, what's the doubt?
Yeah, ma'am. When you showed us the zero vector space, can you refer to that slide?
Yeah.
If we try to in the previous class, you said the dimension is 0 for zero vector space. But I remembered, what will be the span of this zero vector space?
We'll come to that.
Okay.
Okay. It's in the slides. I'll come to that. So everything I'm talking about is a zero space mostly in this lecture. Fine. I'll come to that. Just a bit. Okay. Let's talk about subspace. Okay. What is a subspace? Subspace is basically like a subset of a vector space. Okay. And it has two additional properties that it should follow, that it should be closed under vector addition. So whatever vectors are present in the subset of this vector space, whatever sum or whatever linear combinations are there, they should also belong to that subset or subspace, right? That's all it wants. It is actually just the linear combinations, that their linear combination should also be there. Fine, so we looked at the subspace. Okay, now tell me, if I remove the zero vector from R2, is this a subspace of R2? Why is that? So I have one answer, no. Please tell me the explanation also why it's not a subspace.
The additive identity is missing, so it fails to become a vector space.
Right. So additive identity not present. Right. So because I removed this additive identity, right? This is the additive identity. So this is not a subspace. So this is not even a vector space. It does not contain origin. So it's not a, that's what it translates to, that it does not have origin or the zero vector. Origin is actually a geometrical word. It's not a very linear algebra kind of a word. Okay. When I say origin in geometry, it means the zero vector in the linear algebra. Okay. So basically, I think I have it in the next slide. Yeah. So basically, one should have a zero vector always present to be a space, a vector space. Fine. Here. Or I can say zero vector not present. Fine. Okay. Now tell me, is this a subspace of R2? This I actually proved. Right? This I actually proved. So this is a subspace of R2. Yes. It satisfies all 10 axioms. Also, it's a subset of R2. Fine. Let's move on. So we saw vector space also. and subspace as well. Now next we talked about was basis. So let's see what is basis. So a
Ma'am?
basis is yeah,
Ma'am, I have a doubt, ma'am.
yeah.
Ma'am, every subspace is a vector space, ma'am.
Yes. It
Every
has to be.
subspace,
Yes, it has to be a vector space.
like while defining the basis, you have written that a basis of a vector space.
Yes.
In that case, if every vector space is a subspace, means then why
Okay.
R2 minus 0, R2 minus 0
Okay, tell
doesn't
me. Okay,
doesn't a
I'll give you a,
subspace?
it's a subspace only. Okay. Suppose I have this set 1, 2, 3. Okay. This is a set. Is this not a set? This is a subset of this set, right? This is a subset, right? Subset. But this is also a set. Make
Yes, ma'am.
sense?
Yes, ma'am. Before slide, additive identities have written on that slide.
Where is the additive identity?
Before.
No, no.
While,
All it's saying that this one, right? Subspace.
next
All
slide.
it says that next slide, huh? Additive identity is not present. Yes.
Maybe present or not, ma'am, but R2 is one of the subset of R2, ma'am.
No. So additive identity. So first of all, subspace is also a vector space.
Okay.
Okay, it has to satisfy all the axioms of a vector space. Okay, it's just that it can have lesser
Yes, ma'am.
number of vectors compared to some standard vector space like R2.
Yes, ma'am. Yes, ma'am.
Okay, then it's a proper subspace.
Yeah,
But
ma'am.
a vector,
Before, yes, ma'am.
Yeah.
Before slide, we discussed C into X plus Y, not
Yes.
closed under. Ma'am, actually, it is being closed under multiplication.
where did we discuss
This
that?
one, ma'am. Yes.
This one?
Yeah, ma'am. As you said, ma'am, that the take A as 1 and A2. Like that, I have taken A is equals to 1. Then I got X vector as 1, 4. Y vector
Where
to be.
in over here?
No, ma'am. Next slide.
Okay.
Here only, but you have written C into X plus Y. What I have to.
Into I don't
Next
see a
slide,
C.
ma'am. I think next slide after
Here.
X. Next slide.
Okay.
Here, if here just take A is equals to 1 and I
Okay.
have solved, ma'am.
Mm-hmm.
Then
So
I
it's not
get
coming to.
closed. It's closed under multiplication.
But -1 we saw, no? For -1 it was not.
Yeah, ma'am. Even for -1 also, I'm
Okay.
getting same.
Okay. I'll solve this once myself, and then come back. But when I solved it here, I got a feeling that it's not closed under multiplication.
No, ma'am. Like actually, here you have taken A directly, ma'am. When we got splitted like CX plus CY, then it is being satisfied.
So first of all the properties should satisfied. Okay, should satisfy. If any one of this is not satisfied, then we'll say multiplicative property is not getting satisfied.
Okay.
Okay. So it's not like any one of this is getting satisfied. So I'll say all the multiplicative properties are getting satisfied. So here, I think one property was that when I was multiplying -1 with X, I was not getting the same value.
Why,
Okay, so
ma'am? Here C1 taken as 1, C2 taken as -2, -2 into 1, 1. Same side, both.
No, we
both
solved
values.
this, no? Here, where is that? Here we did, right? So I should get so vectors are all of this form. Okay. So when I did -1 of this vector, I was getting -a, -3a, -1. But b is not equal to 3a plus 1 here.
Okay, ma'am. Like what I saw, like I will share with you and later.
Yeah, we can discuss. Yeah, we'll discuss this offline. But this is not, when I multiply -1 with this, I'm not getting the vector of this form. So it's not closed under multiplication. Fine. Where was I? Yeah, I was here on the basis, right? So, I'll come to your question one. So let me define basis first. So basis of a vector space is a collection of vectors with these properties. Okay. The vectors are linearly independent and they span the vector space V. Okay. Did I talk about span? I talked about span. Okay. So basically, a basis is a set of linearly independent vectors. And these linearly independent vectors, if I take all the possible linear combinations, which is also called the span, I will get the vector space V. Okay. Basis is that. Fine. Okay. Now tell me what is the basis for zero vector space? What is the span of zero vector space? I wanted to ask what is the basis of zero vector space? What spans zero? Yeah. Okay. So what is zero vector space? This is just this. I have zero vector. Okay. Give me an intuitive answer. What can be the basis of zero vector space? Okay. Somebody said, if this is there, is this linearly independent? Basis only contains linearly independent vectors, right? So I cannot take, can I take this vector in the basis of zero vector space? Yes or no? No, no, right? So 0 is not in the basis of the zero vector space. So what will be the basis of this? It will be just an empty set. Yeah, by definition, this is linearly dependent. So we can't take. So it's just the empty set. Understood?
मैम एम्प्टी सेट ऑफ वेक्टर्स को क्या हम लोग वैसे लिख सकते हैं मतलब जैसे मतलब फर्स्ट एंट्री इज 0 लाइक फर्स्ट एंट्री इज एम्प्टी सेकंड एंट्री इज एम्प्टी
No, 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 you can't. You will
So
have
if
to
it
write
is a-
this.
okay,
So there
if
is no vector. Yeah.
if it is empty, then by multiplying any linear combination, like by taking any linear combination of emptiness, how can you generate a vector which has 0, 0?
So you're saying span of what is giving me 0?
Yes, yes.
Okay. So
You're
span of
multiplying
nothing.
scalar. Yeah.
So
Yeah.
first of all, okay. First of all, tell me. Okay, I think I should have said this first. That when I think about span, right? It's actually some space where some magnitude and some direction is there, right? Whenever we were discussing span, I was always asking, okay, what does a span look like? It looks like a line. It looks like a plane. If something is spanning 0, what is 0? There is no magnitude. There is no direction to it.
Ma'am, can't we think of it like a point? The
It's a
same
point, but
analogy.
it's not a vector. But it's not a. But do you have a direction for zero vector? Suppose I draw it here. So it's a very special vector. I have 0, right? This is my 0, 0 vector, 0 vector. What is the direction to it?
No such direction.
There is no direction to it. So this is a very special vector, which nobody can span. Or this space, nobody. So only emptiness can span this.
Ma'am, actually, for zero vector, like the purpose of a vector, जिसके लिए उसका मैग्नीट्यूड और डायरेक्शन दोनों होता है लाइक सपोज 2,4 इज अ वेक्टर बचपन में हम लोग लिखते थे 2i कैप प्लस 4j कैप वेक्टर हम लोग को एक जगह में लेके जाता है
correct it takes you to a particular point. Yeah,
so when we are talking about zero vector, it will take us to where we are already are. So why do we need a direction? Like even without the direction, it will suffice all the conditions. So like not having the direction, will it matter in any case?
No, so usually we assign a concept of magnitude and direction to it. And when I talk about span, right, I talk about a space that is being generated using the linear combination of those vectors. Okay, but 0 itself is not that space, or like you said, it's not taking you anywhere. It's just a point. Wherever you were, you will stay there, right? So what vector can do that? Nothing. Like, you can basically a empty vector or an empty set is which can span 0. Do you get that? I think it's very subtle to understand. But in terms of technicality, okay, let's solve this technically. It's sometimes hard to visualize this, but technically, if you think about it, 0 vector space is there, right? Basis, what is basis? It should be a set of linearly independent vectors, correct? Do I have any linearly independent vector in this particular set?
No, ma'am.
No. So what is remaining is the empty set. So that will be the basis for 0 vector space. Make sense?
Yeah, in this way it makes sense. But when I'm thinking of it in the definition, the usual
In a geometrical sense, yeah, I get that it doesn't make sense that much. But so the way we look at it is usually technically only. That's the only way I can definitely define it. Otherwise, it's very difficult to define what is a 0 vector space or a 0.
Actually, ma'am, what is bothering me is the linear combination part. I'm not looking at the geometry at all. So I'm just going by the definition of linear combination. I'm looking for
Yes.
a scalar C. After multiplying it with nothingness, it will produce me 0, 0. Like in R2. In R2, I'm talking about 0 vector. So I'm looking for a scalar which I can multiply with the nothing vector. I can get a 0, 0. So I cannot think of any such a vector, like any such scalar.
Yeah, I think that definition, right, will not apply here. And only way to look at this is from the point of number of linearly independent vectors in the set. I get it where you're going, that you're trying to take a linear combination of some vector, which will give you a 0. Or if you do C, all C is to 0 and you do some element or some vector is there, then you take the linear combination of that is to be 0. But what I'm saying is, there is no such vector in the vector space, because if the moment you take 0 into your basis, it doesn't stay a basis because it's a linearly dependent set once the 0 get added.
Okay, ma'am. So is it like this, that nothing generates 0 vector? That means nothing is generating 0 vector. So it is becoming the basis.
So linear combination of nothing, only the trivial linear combination of nothing will give me a 0 vector is what it is. But if you change your angle of thinking, right, it'll become, I think you understood that part, that I have only 0 vector in this particular set, and 0 vectors is linearly dependent. So what is left is an empty set for me to be the basis of this vector space.
Okay.
Makes sense? It's slightly subtle, very non-technical, not very explainable, but if you go technically, then it makes sense.
Yeah, ma'am.
Okay. If you're still not satisfied, we can chat after the class. But others, clear that why the basis for a 0 vector space is empty set. I actually have a book that defines that. Let me see if I can find that. Okay. So I was referring a book for this, and it says the same thing, that that if I take 0 vector into the basis, it doesn't remain a basis. So I have to agree to the fact that an empty set is the basis for 0 vector space. Okay, so this is something that you have to remember, that okay, I cannot have a linearly independent set of vectors defining for me a 0 vector space. So an empty set will be my basis for the 0 vector space. Fine. Clear, everyone? I'm not seeing a lot of yes. Clear. Yeah, we'll discuss this after a class. Fine. So I have covered the basis as well for today. Now, the only part left that we covered was the dimension of the vector space. So the number of vectors in the basis of the vector space is called the dimension of the vector space. Correct? So now tell me, what is the dimension of the zero vector space? Right? So dimension of Z is 0, right? Because the basis is empty. Because basis is empty. So we don't have any vector in the dimension. We don't have any vector in the basis of this. So the dimension of zero vector space is 0. Fine. So we have covered all of these things so far, right? So let me draw a big picture for you. Okay. Actually, I have a reference picture that I made. Okay. So I start with a collection of vectors where I have v1, v2 up to some vk. Okay. And I say this is a vector space. Okay. Though I started with a vector and later on defined to you what is a vector space, but let's start with the vector space. Okay. Now, if I take a set of linearly independent vectors, vectors that span V. What is that? Any set of linearly independent vectors that is spanning V. What is that called? Basis, right? So this is called basis. Fine. If I take number of vectors in basis, yeah, what is it called? It's called dimension. It's called dimension. Dimension of vector space. Okay. Fine. I can take some subset of vectors, right? And I can take their linear combination. Linear combination. What will it give me? I'm taking a proper subset. It will give me a subspace. And they will span, right? Spanning a subspace. Spanning a subspace. Fine. Now, if I take linearly independent vectors in this, vectors spanning this subspace, what will it be? Basis of the subspace, right? So this will be basis of the subspace. Right? And then if I take the number of vectors in the basis, that is dimension of the subspace. Fine. So this is the big picture that we talked about. And we have some vectors. And usually that vector follows some 10 axioms and that 10 axioms. And that forms a vector space. If I take a set of linearly independent vectors which span V, that set of vectors is called basis, and we can have multiple bases, right? Multiple bases can be there. And number of vectors in the basis is called dimension of the vector space. Similar thing happens on the subspace tree, that if I take subset of the vectors such that they span some space completely, that space is called subspace. This is actually subspace and not this. Let me erase this. Yeah. And if I take the linearly independent vectors spanning this whole subspace, it's called the basis of the subspace. And if I take the number of vectors in that, that is called the dimension of the subspace. So this is what we have learned so far. Fine. Okay. I have a DTP for you. So this was supposed to be like a revision lecture, but I have now some questions to ask. Okay, this is question. I have V is a vector space. And S is a subspace of V. Fine. What can you tell me? Can we tell about the relationship between dimension of V and dimension of S? Okay, you already interpreted the question. Okay. Can I have more answers? So one answer I have is dimension of V will be greater than equal to dimension of S. Any other answers? Or we'll go ahead with this answer. Nobody is also saying the same answer. Okay. So I have correct only, right? So this is correct. This is correct. So dimension of V is greater than equal to the dimension of S. So this is one question. Now let me ask you another question. Let V1, V2, Vk be vectors in a vector space B. Okay. Can I say that every non-zero vector of V is part of some basis? If no, give example. So I have an answer. No, but I'm waiting for the example. No. So what I'm saying is that I have some k vectors, okay, in a vector space. Can I say that every non-zero vector of V is part of some basis? Some basis. I'm not saying that it's part of this particular basis. Some basis. Right? Others, please answer. Right? So this is not true. This is true. So we have multiple bases, right? If you can imagine this is very good. That I think you have understood the concepts very nicely. That every vector apart from the zero vector, because once we add zero vector, it becomes linearly independent set. Every vector apart from zero vector will be part of some basis set of the vector space. Okay. Because every vector chance to become, every vector will be linearly independent corresponding to some other vectors, right? So this is clear to us. Nice. Okay. Rest I will give you in quiz. I'll give you more tricky questions in the quiz. This is your daily practice problem. Let me define it for you. Let S be a linearly independent subset of vector space V. Okay. Suppose that there is a vector beta in V, which is not present in span of S. Okay. So it's not in S. So if I do the union of this vector beta, which is not present in S, and whatever the subspace S I have, is it linearly independent or dependent set of vectors? You have to do this as the PP and you have to give me a reason why this is so. Okay. So let's not spoil it further. Please solve this question. We'll discuss this tomorrow. And that's all I had for lecture today. Tomorrow we'll probably start a new topic. So I'll end this. So today, this is what we learned. We did a quick recap of everything and we saw a big picture. We also talked about zero vector space and zero vector in detail, respect like in regard of every topic that we studied. Yeah, and that's all I had for today. I'll stop sharing so you guys can ask your questions.